Given a graph G, a vertex X is called a cut vertex if deleting that vertex causes the graph to become disconnected. Similarly, an edge is a bridge if deleting that edge results in a disconnected graph. In greater generality, given any subset of vertices, we're going to refer to that as a cut set if removing those vertices disconnects the graph. Similarly, giving a subset of edges, we will call that an edge cut if deleting those edges disconnects the graph. Finally, the connectivity of a graph is the size of the smallest cut set, so the fewest number of vertices such that their removal makes the graph disconnected. Similarly, the edge connectivity is the size of the smallest edge cut, so the fewest number of edges you have to remove in order to disconnect the graph. So the connectivity is labeled as kappa of G, and the edge connectivity is kappa prime of G. And we will say that a graph is K connected if its connectivity is at least K, and it's K edge connectivity if its edge connectivity is at least K. In other words, a graph is K connected if and only if deleting any K vertices does not results in a connected graph. And is K edge connected if deleting any K edges results in a connected graph. Note that if you check these definitions for the complete graph, you discover that no amount of deleting vertices results in a disconnected graph. So in order to make theorems work out properly, we define the connectivity of a complete graph to be n-1. So first we will discuss Whitney's theorem. Given any graph G, the connectivity of the graph is bounded above by the edge connectivity, and the edge connectivity is bounded above by delta of G, the minimum degree. So this is saying that any minimum edge cut has at most the same number of edges as the smallest degree vertex. So we will start first by proving this right inequality. So suppose your graph has n vertices, and suppose the minimum degree is k. So we want to find an edge cut of size k. Well, one way to do that is to take a vertex of degree k, and then just consider the edges incident to that vertex. So we're going to let that set be known as f, and we see that g minus f is disconnected. And the reason why that is because if we take a vertex of minimum degree, and we delete all the edges incident to that vertex, then we discover that there's no way to get from that vertex to any other vertex in the graph. Thus, we see that the edges incident to a vertex always forms an edge cut, and therefore the smallest edge cut has to be at most the minimum degree. So now we want to show the other inequality. So this says that given any minimum edge cut, somehow we should be able to find a vertex cut set that's smaller. This part is going to proceed in stages. So first, suppose we have the complete graph. By definition, we've defined its connectivity of a complete graph to be n-1, and that happens to also be the minimum degree. We can also show that that has to be the edge connectivity, which is currently a gap in the proof that we will fill in a little bit when we do one of the cases for the more general argument. So we still need to show that the edge connectivity is also n-1. But for now, suppose you do not have a complete graph. So this means that there exists two vertices that don't have an edge between them. Then a lot of the rest of the proof is going to be finding a way to disconnect those two vertices from each other. So suppose we have a minimal edge cut f, and we're going to let g1 and g2 be the components of g minus f. So first, suppose that between any vertex in g1 and any vertex in g2, we have the edge. So in other words, we've designed our edge cut so that all the possible edges between these two sets exist. Then the number of edges in our cut is the size of g1 times the size of g2. And g2 is n minus the size of g1. And after this proof is over, we will prove that this product is always at least n-1, as long as one of these two sets has at least one vertex in it. And so in this case, we see that the edge connectivity has to be at least n minus 1. It's also worth noting that this fills in our gap earlier because given a complete graph, if you take any edge cut in a complete graph, we have exactly this situation where every pair of vertices with one end and one component has to be connected by an edge. So for the rest of this case, we're back to assuming G is not a complete graph. Then that means one of these components can't be complete because we're missing an edge, and it can't be the edge in the cut that's missing. So suppose it's G1 that's missing an edge. Let's take the two vertices in G1 that do not have an edge between them. Then if you delete every vertex except those two, you're going to get a cut set of size n minus 2 because you've deleted all the vertices but 2. And you've separated x from y since they don't have an edge between them. So we found a cut set of size at most n minus 2, so the connectivity number is at most n minus 2, but that's less than n minus 1, which is the edge connectivity. So that finishes this case. So in our remaining case, there has to be a missing edge between G1 and G2. So an x in G1 and a y in G2, where the edge between them does not exist. So we want to find a cut set with fewer vertices, at most the same number of vertices as the number of edges in this edge cut. And so again, the strategy is going to be to separate x from y. And so we're going to define our cut set to consist of those vertices in G2 that have the property that they're part of an edge with the other endpoint being x. Similarly, we're going to add those vertices from G1 that are adjacent to y. So basically, it's the neighborhood of x and the neighborhood of y with respect to this cut set. So we need to show that this is a cut set, and we need to show that it has size less than the size of our edge cut. So to show that second fact, consider the function from our claimed cut set to the edge cut by just sending every vertex to an edge. So f of u is the edge xu if u was in G2, because by construction, these vertices are adjacent to x. And otherwise we send u to uy for u in G1, because for s is defined, we define the vertices in S intersect G1 to be the neighbors of y. And in particular, this function has to be injective, because the only way you could get the same output twice is if xy were an edge, but it's not. So we see distinct vertices have to map to distinct edges. In particular, that means the size of our cut set is smaller than the size of the edge cut. And remember, this is a minimum edge cut. So now we need to see, I give the rest of the argument, but it's worth pointing out that you've basically separated x from y because you've removed all the neighbors. So you know it's not possible to get from x to y because it's not really possible to get from x to anything else. And so we see that the connectivity of G is at most this size, S, which is at most the size of our edge cut, which we define to be a minimum edge cut. So there was one gap in the proof, which was in case 1, this idea about this product of two sets, their sizes being at most n minus 1. So the claim is that whenever k is a positive integer between 1 and n, not including n, then we have this inequality that k times n minus k is at least n minus 1. Note here, the reason why we don't allow k equal to n is because, remember, we've separated n vertices into two groups. And the fact that there has to be at least one vertex in each group means that k can't be equal to n. So we want to show this inequality. So let's take the difference on both sides. And so we're looking at k times n minus k minus n plus 1. Then the clever trick is to cleverly add and subtract k. And if you do that, then you can rewrite this minus n plus k as minus parentheses n minus k. and this minus k plus 1 is minus parentheses k minus 1. These first two terms have a common factor of n minus k, so you can factor that out and you get k minus 1. Now what's left over has a common factor of k minus 1, so you can factor it again. And so this thing is equal to k minus 1 times n minus k minus 1. Since k is at least 1, this first term is non-negative. And since n is strictly bigger than k, you can check that n minus k is strictly positive, so n minus k minus 1 is also non-negative. The product of two non-negative integers is non-negative. And so this expression is at least 0, which means k times n minus k is at least n minus 1. All right, so here is another proposition. We're going to say a vertex z is a cut vertex in a graph G if and only if there exists two vertices x and y, such that every path between x and y has to contain the vertex z. Note that in red I also state a corresponding version for edges. An edge is a bridge if and only if there exists vertices x and y such that every xy path contains the edge z. However, that proof will be left as an exercise. We're only going to prove the case for the vertex being a cut vertex. So first, suppose we have a cut vertex. Then we know when you delete the cut vertex from the graph, you're going to get two components, C1 and C2. Then what we're going to do is just take a vertex in each component. X in C1, Y in C2. I should note for all these proofs there could be other components, but the main point is there's at least two. So we've got two vertices X and Y. And in the original graph, they have to be connected by a path. So there's at least one path. Consider any path between X and Y, say P. Then since X and Y are in different components, if the path was in G minus Z, then it would turn out that that means X is path connected to Y, and they're in the same component, which is a contradiction. Therefore, it must be the case that this vertex Z actually appears on that path, and thus every path between X and Y has to contain the vertex Z. Now let's prove the converse. Suppose we found two vertices X and Y such that every XY path contains the vertex Z. Then that means that there is no path between X and Y and G minus Z, which means that X and Y have to be in different components in G minus Z. So that means G minus Z is disconnected, which means that Z is a cut vertex. So to end this video, we'll mention two other theorems that are often given as homework exercises. The first is that every non-trivial connected graph has at least two non-cut vertices, which is useful for induction proofs because it means you could do a proof by induction by a connected graph, knowing that you have at least one non-cut vertex you can delete, such that the deletion is still a connected graph. Similarly, if you're interested in edge connectivity, the corresponding version for edges is that an edge is a bridge if and only if it is not contained in any cycle. So in other words, if you have a connected graph and it's not a tree, you're guaranteed to find an edge that's not a bridge so that you can delete that edge and the result is still a connected graph. So that allows you to do induction proofs on the number of edges in a connected graph.